Hi everyone. In this video, all of our hard work from previous videos will pay off when we are finally able to define the Lebesgue integral of a bounded function. So we will define the Lebesgue integral of a general bounded function. We will look at what exactly that definition means. We will then explore connections between the Lebesgue integral and the Riemann integral, as well as beginning to look at some properties of this new Lebesgue integral. So recall from the previous video that we proved this theorem about essentially an alternate sort of definition of measurability. So we said, suppose that f is a bounded real-valued function on a set E of finite measure, then the infimum over all simple functions psi that are greater than or equal to f. So the infimum over that set of the integral over E of psi is equal to the supremum over all simple functions phi less than or equal to f of the integrals of those phi's. So that infimum is equal to this supremum if and only if the function f is measurable. Now, again, I've sort of described this as sort of an alternate definition. It's not quite an alternate definition because this only applies when f is a bounded real-valued function, whereas our actual definition of measurability does not require that f be bounded. But at least for bounded real-valued functions, we can, on sets of finite measure, we can think of this as being some sort of equivalent definition. Now, what I want to do is I want to sort of look at this first, though, and think about each of these quantities. So I first want to think about sort of this infimum quantity, and then we'll likewise think about the supremum quantity here. If I think about this infimum quantity, then let's see, what is this really getting at? So I'm taking all of these integrals. So I'm taking the Lebesgue integral over the set E of this function psi, but psi is a simple function that is greater than or equal to some measurable, or not measurable, but just some function f. Okay, so you can imagine that I have, say, some function f, right? Maybe it looks like this. Okay, and I have a set E. Just to make my life a little easy here, E need not be an interval, but let's just sort of think of it on some interval AB. Okay. And so what does one of these functions look like? So again, psi is a simple function. It's greater than or equal to f. Well, here is maybe one such example. Sorry, let me swap these around. So here is a simple function. It's greater than or equal to f. This is actually not quite a step function, right? Because we take on this value not on an interval, but only at a single point. Of course, you could do much more sort of exotic things. So for example, between here and here, say between these two x values, you could define it to have this height, whatever this is, y1, if x is in this interval, intersect the rationals, and you could define it to have some other value y2 in between there. Again, it just needs to be a simple function. It doesn't have to be a step function. So here's an example of one such set. And the idea is, for a simple function, I have already defined, right? So if this is an example of a function psi, I've already defined what this is, right? We already defined the Lebesgue integral of psi over the set E, and it is, by definition, the sum k equals 1 up to n of a sub k times the measure of a sub k. We're generally here, right? This a sub k, if we're doing the canonical representation, a sub k is just the preimage of a sub k under psi. Okay. So I can take this simple function. This simple function is greater than or equal to f everywhere, and I can calculate its Lebesgue integral. Okay. Well, what I want to do is I want to do that, but I want to do that for every simple function psi that's greater than or equal to f. So I do it for this one, but then I can do it for some other one. Right? And you can imagine, like, if you look at this, if you think about psi as maybe being some sort of approximation of f, well, first of all, it's always going to be an overestimate of f, right? Because we've intentionally made psi greater than or equal to f. Um, but also, like all of these Lebesgue integrals, they're going to be greater than or equal to whatever I would want the Lebesgue integral of this thing to be, right? They're overestimates, right? So what I think about is I want to take every simple function that's greater than or equal to psi. For every one of those simple functions, I can calculate its Lebesgue integral. And then look at that collection of values you get back. So that collection of values, right, is this set that you're taking the infimum of, right? So the idea is, one way to think of it is sort of like you want to think about simple functions that are getting closer and closer to f, but they're coming from above, right? So all the integrals are going to be overestimates, but you want to get the least up, or sorry, the greatest lower bound of that set, right? Should sort of tell you how these simple functions are settling down to approximate f. Now, that should remind you of what we did with Riemann integration. When we did Riemann integration, right, we defined an upper Riemann integral in exactly this same way. The only difference was there we were taking infimums over sort of Riemann sum, upper Riemann sums, lower Riemann sums, or upper sums and lower sums. So that seems a little bit different, but the idea is really exactly the same. Okay, those Riemann sums, right? They were of the form. So if I took an upper sum, so that was an upper sum over of the function f over a partition P, then we said this was the sum capital M sub k times delta x sub k, where capital M sub k was just defined to be the maximum over x sub k minus 1 to x sub k of f of x. Okay, so you could really think of this as being sort of some function value times this delta x of k. That was the length of my interval, right? So you could really think of this as like a capital M sub k times this was the length of an interval. That's the same as the measure of the interval x sub k minus 1 to x sub k. So again, very similar. The only difference really here is that you're sort of forced here to work on step functions, really, right? These functions have to be constant on an interval, whereas here they just have to be constant on some set, but this isn't required to be an interval. Okay. So in exactly the same way that we defined upper, so then for the upper integral, right? We just said that the upper Riemann integral right, was just the infimum over all partitions P of the upper sums of that function. Okay. All right. Now, this quantity then, right, this is really a very similar type of thing. It's an infimum over all of these functions that are simple functions, which are greater than or equal to f of these integrals. So, and these integrals, because they're integrals of Lebesgue integrals of simple functions, they're really just sums, right? So in a way, this quantity in the orange box here that we're looking at, this is sort of like an upper Lebesgue integral. Okay. Now, similarly, if we look at this thing on the right, look at this quantity here. So if I look at this quantity, similar idea, but now I'm looking at functions phi that are less than or equal to f. So I could look at, say, something like this. There's a simple function phi that's less than or equal to f. Okay. But I do, for every simple function that's less than or equal to f, I calculate this, the Lebesgue integral of those simple functions. Again, those are going to be defined in exactly the same way. The only difference here is that I'm looking at simple functions less than or equal to f instead of greater than or equal to f. And then I say, well, each of those integrals should be some underestimate of the true Lebesgue integral, because all these functions are lying below f. So I want to take the supremum of all of these integral values that I get back. Now, again, if you think about this, this is something like a lower Riemann sum, right? Or sorry, a lower Riemann integral. So this is like a lower Lebesgue integral in some sense. Now, if we think about it in that way, notice what this is saying. This is saying that f is measurable if and only if something like the upper Lebesgue integral is equal to the lower Lebesgue integral. Well, really, the upper Riemann integral being equal to the lower Riemann integral, that's how we defined Riemann integrability. So in some ways, what this theorem is saying is a function is measurable if and only if it's Lebesgue integrable. Okay. So the way we actually want to define Lebesgue integrability is we'll say let f be a bounded measurable function defined on a set E of finite measure. The Lebesgue integral of f over E is defined by the Lebesgue integral of f over E is equal to this infimum. Now remember, this is precisely what had been sitting. If I flip back, right, this is precisely the value that had been sitting over here, right? So if my function is measurable, these two values will be equal. If they're equal, then I might as well think of my function as being Lebesgue integrable. Oops. And therefore, the value of the, I can just take the value of the Lebesgue integral to be that common value. I could just as easily put the soup over here, right? But it doesn't matter, right? Because these are going to give the same thing in either case, right? All right. So the idea really is you have these sort of approximating simple functions from above, approximating simple functions from below. When your function is measurable, that's precisely when those two are equal to each other. And then we just define that common value to be the integral, the Lebesgue integral of f over E. Now, we have now defined, right, we have defined a new type of integral. And sort of the first immediate question you might ask yourself is, well, what on earth does this have to do, if anything, to our previous notion of integration, right? Well, right, we've already sort of noticed this a little bit, right? When we notice that since every step function is a simple function, then somehow like approximating things by step functions, that's a special case of approximating them by simple functions. Additionally, if we think back to sort of what Lebesgue's stated goal was in developing this integral, it wasn't to sort of redefine integration, it was to expand integration to the largest class of functions possible. So a reasonable question, as soon as we have this definition in hand, is sort of, well, what, if anything, like how does this relate, if at all, to Riemann integration? Now, what would we like? What we would like is we would like for every function that's Riemann integrable to be Lebesgue integrable, right? Because if not, then that means you're losing some things being integrable in order to have this new definition of integrability. Now, there might be good reasons to do that, but it would sort of work against our Lebesgue's stated goal of expanding the notion of integrability if we were losing things. So we'd like all the Riemann integrable functions to also be Lebesgue integrable. And then we might also wonder, maybe every Lebesgue integrable function is Riemann integrable. But of course, they're not. We've already seen that. The characteristic function of the rationals is Lebesgue integrable, but not Riemann integrable. So we can only sort of hope that all the functions that are Riemann integrable are Lebesgue integrable. Now, further, what would we like? I'd really maybe even like those values to be the same, right? If I have a function that's both Riemann and Lebesgue integrable, I might like the value of the Lebesgue integral to be the same as the value of the Riemann integral, right? And in fact, this is one of those cases where exactly what you might hope for is true. So we want to prove this theorem. So the theorem says let f, so I want f to be defined on an interval AB into R. I want f to be bounded and Riemann integrable on that same interval AB. Then I'll show that f is measurable and the value of the Riemann integral of f from A to B is the same as the value of the Lebesgue integral of f over the interval AB. Okay, so again, this says exactly, it's like all we could sort of hope for, right? If I have a Riemann integrable function, f is measurable. Remember, measurable really is saying like Lebesgue integrable, right? And the value of the Lebesgue integral over that interval AB is exactly the same as the value of the Riemann integral. So this says sort of like we've done it. We've accomplished what we set out for, which was to expand but not change the notion of integration. So we've expanded it to new functions without changing the values of the integrals on any of the Riemann integrable functions. Okay. All right. Now, before the proof itself is sort of quite short, but I think it takes a little thinking through. Okay. So what this really gets back to is this notion of, so we're first just going to sort of sketch out some ideas, right? So this really gets back to that notion we were talking about earlier, right? So if I look at the supremum over all simple functions less than or equal to f, and just for the second here, I'm actually going to write sort of as part of the subscript here that phi is simple. So if I look at the supremum over all simple functions phi with phi less than or equal to f of the integral of phi, in this case, over the interval AB, d mu. Now I want to think about how does this compare to the supremum? What if I just change, instead of looking at simple functions, what if I just look at step functions? Well, the first observation that I'll make is that the set that I'm taking the supremum over here contains this set, right? Every step function is also a simple function, but not every simple function is a step function. So I'm taking a supremum over a set here, but it's a subset of this set, right? Now what happens if I take supremums, but I look at a subset, right? That makes my supremum potentially smaller. Okay. So these compare in precisely this way. Okay. Now, on the other hand, if I look at infimum, so I look at that other sort of quantity, I look at the infimum overall psi greater than or equal to f, where psi is a simple function, the integral over AB of psi d mu. If I restrict the set, now my infimum possibly gets larger. If I look at just overall step functions that are greater than or equal to f, I get potentially a larger infimum. All right. Now, what I want to think about is how do these quantities relate then to upper and lower Riemann integrals? Okay. Well, it turns out here, right, that if I think about, so think about, if I write in, I sort of think this should be sort of similar to a lower Riemann integral. Okay. And that, of course, is defined to be the supremum over all partitions P of lower sums. Well, saying I'm looking over every partition P, okay, and I'm looking over every partition P, and these things are really these lower sums look like this. Okay. Now, this is not the same. This is not quite the same as this. Okay. But if you think about what's going on here, so this integral here, right, because this is a simple function, this is defined to be a sum ak mu of ak. But of course, there's no requirement here that this be there's no requirement here that like this be somehow have a minimum value of the function, right? This definition sort of ties it intrinsically to the function values. This doesn't really, right? This allows phi could be, or phi could be any step function lying below there. Okay. However, what I can say for sure, right, is that each of these sums can be thought of as one of the step functions that appears in here. Okay, right. So if I think about one of these particular lower sums, right, it is essentially the integral of some step function. It's the Lebesgue integral also, some step function that lies below f. So, well, I can't exactly say these are equal to each other. I can certainly say this is less than or equal to, right? Because again, I'm looking here now over some subset of all step functions, right? So this is, well, this supremum is greater than or equal to the um, lower Lebesgue integral. Now, a nearly identical argument can be made to show that this is greater than or equal to the upper Lebesgue, or sorry, the upper Riemann integral of f. All right. Now, it's also worth noting, and again, if I look at these two quantities, right, because of these requirements, basically that the phis are always less than or equal to f and the psi's are always greater than or equal to f, these are ordered in this way, okay? And so what we're actually going to use to prove this theorem is the fact that the lower Riemann integral is less than or equal to this quantity, which is less than or equal to this quantity, which is less than or equal to the upper Riemann integral. Okay, so we're going to prove this. The book just sort of states it, right? The book says, well, you know, this is less than or equal to this, less than or equal to this, less than or equal to this, and then the proof falls out very quickly. But understanding this takes a bit of justification. All right, so now we can erase. We'll rewrite sort of the punchline of that in our proof, but this really gets us. It's really 90% of what we need then to prove the theorem. I sometimes think I should go through and cut out all the time of me erasing the board. But I hope that either you can speed through it, or it's maybe a good point for you to sort of make sure you have some time to catch up with writing in your notes. But maybe if this is really bothersome, you can let me know, and I can, before I teach this course again, I guess I could go back and cut out some of the blank space of just me erasing. All right. So how does the proof go? All right. So then here's the proof. Now, the way the book states it is essentially since every step function is a simple function, then we have, and now I'm just going to write down this series of inequalities we just had, cutting out sort of the middlemen. So again, this is sort of what we had in that first line, and then is less than or equal to. So in the second line, we had the infimum over psi greater than or equal to f psi simple. And then on the second line, we had that this was less than or equal to the upper Riemann integral of f of x dx. All right. So now, what do we know? We're supposing that f is Riemann integrable. Well, since f is Riemann integrable, what does it mean to be Riemann integrable? Well, to be Riemann integrable means that the lower integral is equal to the upper integral. Okay. So the lower integral is equal to the upper integral. Okay. But now if these two are equal, then these two must also be equal because they're squeezed in between these two. So thus, the supremum of the lower simple functions just a lot of notation here, has to be equal to the infimum okay. So these two things have to be equal to each other. And not only that, they have to be equal to whatever this common value is, which is just the value then of the integral from a to b of f of x dx, the Riemann integral. Okay. Well, these two being equal, right, means f is measurable. And then the value of the Lebesgue integral over the interval AB of f d mu, it's just equal to this infimum, which is just equal to the Riemann integral value. So again, what we've done here is establish that if our function is Riemann integrable, it must also be measurable, right? And it's measurable because this supremum is equal to this infimum. And then once it's measurable, then the value of the Lebesgue integral has to be this common value, but we also showed that this common value was just the value of the Riemann integral. So when your function is Riemann integrable, not only is it Lebesgue integrable, but the values of the Lebesgue and the Riemann integral agree with one another, which is, again, sort of as much as you might possibly hope for, right? All right. So that's really nice to have, because if you think about it, this is then a huge step in calculating calculating Lebesgue integrals, which is if it's Riemann integrable and you want to calculate the value of the Lebesgue integral, just use Calc 2, right? That's all of Calc 2 was really methods for finding Riemann integrals. Well, now you know that you can use all of those same tools to finding Lebesgue integrals as long as your function was already Riemann integrable. All right. Now, the next theorem, we're not going to prove all the parts of this, but let me just sort of point out that this Lebesgue integral satisfies all of the same properties that Riemann integrals do in many ways. And in fact, some of them are a little nicer in some ways. So the first two properties, right, are just linearity of the Lebesgue integral. So I can pull constants outside of Lebesgue integrals, and I can break up Lebesgue integrals over sums. Now, of course, as soon as you can do both of those, you could also do differences. right? Because I could think of that as f plus -1 times g. So I could do differences, right? I can break these integrals up in the normal way. Okay. Now, 3 and 4, these ought to look very similar to things we have for Riemann integrals, but they're actually, in some ways, a little bit better. So if f is less than or equal to g almost everywhere, so let's recall what that means. That means f is less than or equal to g, except possibly on some set of measure 0. So f doesn't even have to be less than or equal to g everywhere. It's just that the measure of the set of places where f is not less than or equal to g must be small. It must have measure 0. Okay, so if f is less than or equal to g almost everywhere, then the Lebesgue integral of f must be less than or equal to the Lebesgue integral of g. Okay. Similarly, if f is equal to g almost everywhere, then the Lebesgue integral of f is equal to the Lebesgue integral of g. Now, in particular, let me point here, what this does is actually, in some ways, you could view this as either a pro or a con of the Lebesgue integral. Now, keep in mind, right, for Riemann integrals, right, if f is equal to g, then the Riemann integral of f is equal to g. It is possible for Riemann integral, if you change some finite number of points, certainly, right, that's not going to change the value of the Riemann integral. But what this is saying is you could potentially have f and g have different values on an uncountably infinite set as long as that set has measure 0, right? So you could have two functions that are not equal over the rationals, but are equal over the irrationals. Their Lebesgue integrals will have to be the same. Now, again, one way to view this is it's sort of a robustness of the integral, right? You can play around with a whole bunch of different points. It's not going to change the value of the integral. On the other hand, another way to view this, so that's viewing it maybe in a positive light, right? This is very robust. Even if I change my functions at a bunch of points, like as long as the sort of measure of the set of points where I change it isn't too much, it's not going to change the value of the integral. On the other hand, you can view it as sort of a lack of sensitivity, right? The Lebesgue integral is not able to differentiate between two functions unless they are different on, it certainly has to be more than a countable set, right? Because any countable, if they only differ on a countable set, that would be a set of measure 0. So again, I just point this out. This works both ways. Sometimes this is really nice. It sort of means the Lebesgue integral is really robust and you don't have to worry about it changing if you change a bunch of points, as long as the set of points where you change it is not of positive measure. On the other hand, it sort of reflects a lack of sensitivity, that you sort of lose some information when you integrate these things, and it's not able to differentiate between functions that could be different on an uncountable set. All right. The fifth property, really, this again is very similar to what we have for Riemann integrals. So we prove something just like this. So if your function f is bounded between two constants, little m and capital M, then the integral must be bounded between little m times the measure of e plus capital M times the measure of e. Here, for Riemann integrals, we replace this with b minus a, again, because if you're doing a Riemann integral, you're integrating over an interval, but a measure of an interval is just its length, so replacing that with b minus a is fine. Okay. Now, this last property, we also have an equivalent version of this for Riemann integrals, although you might not realize it at first. So this says if E1 and E2 are disjoint measurable sets with E1 union E2 equal to E, so one way I think of this is E1 and E2 partition E, right, into two pieces, then the Lebesgue integral of f over E is equal to the Lebesgue integral of f over E1 plus the Lebesgue integral of f over E2. Now, this is equivalent to, for Riemann integrals, the theorem that says the integral from a to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx. Right? Now, notice, right, if I'm doing Riemann integration, then I'm integrating over an interval. And for each of these pieces, right, for a Riemann integral to make sense, I have to have intervals here as well. So the only way to partition an interval into two disjoint intervals is to just pick a C value in between and partition it that way. However, for just measurable sets, right, there are lots of weird ways you could partition them, right? So you could take all the reals and partition them into the rationals and the irrationals, right? That is partitioning the reals into disjoint measurable sets, right? And then you can integrate over the rationals and you can integrate over the irrationals, and that will give you the value of your function integrated over all the reals, right? So I sort of like this because this is cool. This is cool in that it allows you to sort of partition things in lots of weird, exotic ways. And that can be really powerful sometimes, right? So again, you don't have to just integrate over intervals. You could integrate over the set of all x values where a function has some property, and then integrate over the set of all x values where the function does not have that property. And that has to be equal to the integral of the function over the entire domain, right? So again, this allows sort of neat partitionings that actually become really helpful in doing a lot of higher level analysis. Okay, in areas of functional analysis, this is a really common trick. Now, we're not going to prove these. I'll just point out why do these work, right? Well, essentially they work because if you use they work for simple functions, right? So you can pretty quickly show that for a simple function psi, the integral over e of c times psi d mu, well, what is that? That's just defined as a sum. So this is just c times ak times mu of ak. I can pull the c outside of the sum, right? But this is just defined to be the integral over e of psi d mu. So again, basically what you do is all of these properties work for sums, for finite sums, okay? So you show they work for the Lebesgue integral of simple functions. And then you show that because they work for the integral of every simple function, then they work for the integral of any bounded function. Again, by just showing that basically you can pull these constants out of infimums as well, infimums and supremums. Okay. So it turns out that these are all fairly straightforward proofs. Okay. Now, the last result I want to discuss in this video is another, it's actually a corollary of all of these, and we'll actually prove it really quickly. So let f be a bounded measurable function defined on a set E of finite measure. Then the absolute value of the Lebesgue integral of f is less than or equal to the Lebesgue integral of the absolute value of f. Okay. Now, again, we have something like this for Riemann integrals. So for Riemann integrals, we have the absolute value of the integral of f. The Riemann integral of f from a to b is less than or equal to the Riemann integral of the absolute value of f from a to b. Okay, so we have this for Riemann integrals. And really, both of these are, there's something like triangle inequalities, right? If you think of integration as adding things up, this is saying, if I add all the things up and then take the absolute values, that's less than or equal to if I take the absolute values of each individual thing and then add them all up. Right? Now, the proof of all these, of most of these things follows in exactly the same way. So certainly for the Riemann and the Lebesgue case, it follows in the same way. So all of these work by looking at the observation that I can always bound my function f between the absolute value of f and minus the absolute value of f, right? In fact, for any particular x value, precisely one of these is equality, okay? But in any event, once I have this sort of ordering here, right, then what I can do is note that I can integrate each of these. So by the properties on the previous slide, if I integrate each of these over E, I still get the same inequalities here. And I can use the linearity of the integral to pull this minus sign outside of this integral. So I'll just pull that outside. And now I have that this integral is bounded between some number and minus that number. Okay. So what does that imply? Well, that implies that the absolute value of this thing sitting in the middle, or the absolute value of the integral of f. Oh, sorry, it's not a Riemann integral, it's a Lebesgue integral. This thing sitting in the middle, its absolute value is less than or equal to the integral over E of absolute value of f d mu. Okay. And again, this is exactly in spirit the same proof that we use for showing this property for Riemann integrals, right? You show that because it preserves the inequalities and because of the linearity, you can make exactly this same argument, okay? So what we've seen in this video is the formal definition of the Lebesgue integral. We have observed that every Riemann integrable function is Lebesgue integrable. And in fact, the value of the Lebesgue integral of those Riemann integrable functions is exactly the Riemann integral. And we've begun to see a few elementary properties of the Lebesgue integral. Now, moving forward, we will want to continue to work with our definition of Lebesgue integrability and also expand our ability to look at the Lebesgue integral by looking at the Lebesgue integrals not only of bounded functions, but also of unbounded functions.